Hi, now we are analyzing CSIR December 2013 Chemical Sciences. Just look at the given problems. L-dopa is used for the treatment of tuberculosis, Parkinson's disease, diabetes, cancer. Answer is Parkinson's disease. Okay, just look at the structure of L-dopa, which is also called as levodopa, and here the name, official name or IUPAC name is L3,4-dihydroxyphenylalanine. Okay, L-dopa is used as a precursor in neurotransmitters like dopamine and norepinephrine, which is called as noradrenaline, and epinephrine, which is called as adrenaline. Okay, and here L-dopa is used in the treatment of Parkinson's disease. Okay, right. Next one, in the IR spectrum of para-nitrophenyl acetate, the carbonyl absorption band appears at, okay, just look at the four options, we need to give the correct one. And first thing, we need to draw the structure of para-nitrophenyl acetate. Just look at here, and this is the structure of para-nitrophenyl acetate. One can draw the structures whenever we have given with IUPAC names, then whenever they have the command on IUPAC nomenclature, and just check the lectures on IUPAC nomenclatures in your course. Okay, right. Now just look at the para-nitrophenyl acetate, and here we need to look for this carbonyl group. For that we need to give correct IR stretching frequency carbonyl absorption band. Okay, right. If you look at that carbonyl group which is having adjacent heteroatom, that is oxygen, as we know, which contains a lone pair of electrons on it, right? And just remember that whenever the carbonyl carbon has more electron density around it, then its stretching frequency decreases from its normal stretching frequency of that particular carbonyl group. Okay, just remember that whenever the carbonyl carbon has more electron density, okay, then it has less stretching frequency from its normal stretching frequency. At the same time, whenever the carbonyl carbon has less electron density around it, then it gives a higher stretching frequency than its normal carbonyl stretching frequency. Okay, remember this important point. Now you can give the answer from this explanation here. So the lone pair of electrons on this adjacent oxygen can shared by the carbonyl group. That means the lone pair of electrons on adjacent oxygen goes into the carbonyl carbon, okay, and which is stabilized by that resonance. Okay, at the same time, the lone pair of electrons on oxygen can also share by this phenyl ring, because the phenyl ring is having electron withdrawing nitro group. Okay, strong electron withdrawing group nitro group. That's why the lone pair of electrons are dragged towards this phenyl group. At the same time, some of them drag towards this carbonyl group. That means the electron density around this carbonyl carbon is decreasing, and which leads to increasing its IR stretching frequency than its normal stretching frequency of carbonyl group. Okay, and if you look at all these, simply the highest one is 1770, so that is the correct carbonyl absorption band for this para-nitrophenyl acetate. So here option 4 is the correct one. Okay, right. And if electron, for example, if phenyl group contains electron donating group here on this phenyl ring, then what happens? Electron density moves towards this heteroatom, and the electron density of this oxygen gives, that means it donates, or the electrons from that heteroatom dragged by this carbonyl group, and electron density increases on this carbonyl carbon. So that leads to decreasing in IR stretching frequency. That means from 1772 it decreases further nearly 1700 to 1750, in between that. Okay, right. Just remember those important points for this. Next one, the major product formed in the reaction of styrene with an excess of lithium in liquid ammonia and tertiary butyl alcohol is. Okay, just understand the given information in the problem. We need to give the correct structure, which is given as options here. Right. The first thing, if you look at the styrene structure, which is having one alkene and one phenyl ring. Okay, as we know, a simple alkene can act as a nucleophile, right? And at the same time, a phenyl ring can act as electron withdrawing group, right? In that case, that means the electron density on this phenyl carbon decreases here, okay, because the alkene, terminal alkene, can act as a nucleophile and it is ready to donate its electrons. At the same time, the ring electrons are dragged towards the ring to get the delocalization. That's why the carbon where the alkene attached to the phenyl ring have the lowest electron density. That's why lithium can give its electron to that particular carbon of the phenyl, that means carbon of phenyl group of the particular given styrene, okay. So which simply make it as the product, which leads to the product as a electron withdrawing group. That means whenever the benzene ring has electron withdrawing group, then we can get this kind of reduction. Whenever the benzene ring connected with electron donating group, we can get opposite, just like this compound we can observe, okay, right. If you look at here, it is very important to know that here the two possible isomerization takes place here, okay. Just observe the arrows here, and the isomerization of hydrogens takes place on the double bond, and hydrogens exchange places and to make this styrene, that means reduced styrene, okay. And we have given excess amount of lithium ammonia in tertiary butanol, that means further reduction takes place, and that means here you can see simply butadiene can reduce it to form single alkene, that means single alkenic product you can observe here, right. So this is the final product you can get in the reaction given in the problem. Next one, the major product formed in the following reaction is, okay, just observe the reactants here, and we have given with heat and H2SO4 conditions, and you can see the lone pair of electrons on nitrogen can act as a that means NH2 can act as nucleophile, which is going to attack on this carbon, okay, carbonyl carbon, that means simply anhydride here, okay, right. And next one, just check the mechanism. Simply the lone pair of electrons on nitrogen going to attack here, okay, and then simply on heating, loss of water molecules takes place, okay. We have given with heating and H2SO4. As we know, H2SO4 can act as dehydrating agent, okay. In the next step, the lone pair of electrons on nitrogen goes on to the ring, and the ring electrons attacks on the terminal carbonyl group, okay. And in that case, we have the formation of ring takes place here on that intermediate, okay. After that, to compensate the positive charge on this nitrogen, simply elimination of water takes place here. At the same time, that means the bond breaks from that carbon hydrogen, and the double bond goes onto the nitrogen to make it neutral, okay, right. And at the same time, the elimination of water takes place here, and we can get the final product, okay. Just check the mechanism carefully, just use the arrows here, okay, right. Next one, for estrone, among the statements A and C, the correct one are, it is a steroidal hormone, and it has two hydroxyl groups, it has one ketone and one hydroxyl group, okay. So here we have given with the female hormone, that is estrone, and this is the structure of estrone, which contain one hydroxy group and one keto group, okay, one ketone, one hydroxy group, that means option C is the correct one, and it is a steroidal hormone, okay. Estrone is a steroidal hormone, and you can check all other female hormones like estradiol, just observe the structure here, and progesterone and estriol, okay. So just check all the structures here of for the female hormones. And next one, an organic compound having the molecular formula C10H14 exhibited two singlets in the H-NMR spectrum and three signals in C13NMR spectrum. The compound is, okay. So the first one is the correct answer, because you can see first we need to check for the equivalent carbons and equivalent hydrogens in the particular given compound to find the number of signals, okay, for the H-NMR and C13NMR spectrums, right. So to check that, we need to use a plane or a C2 axis, okay. Plane or C2 axis, if we use, both of them can give equivalent carbons and equivalent H-NMR active carbons and hydrogens here on the particular given molecule. And you can see, you can divide this given first option, the compound 1, into two ways, okay. You can cut by 2 planes here on this molecule. And if you do that, so this is the similar structure you can get in all the possible possible cuttings with the planes. Okay, that means if you observe this one, okay, this one part of the given molecule which gives number of C13 and number of HNMR signals. Okay, if you look for that HNMR signals, so here we have one hydrogen and here CH3 contain, that means carbon contains 3 hydrogens for it, methyl, for that methyl group. So total 2 signals are appeared in HNMR signal HNMR spectrum for this molecule. Okay, because at this carbon we have connected with methyl carbon, that's why there is no hydrogen for it. Only 2 HNMR active hydrogens are there, that's why 2 signals are in HNMR spectrum. At the same time, we need to look for the C13 NMR. In that C13 NMR we have 3 carbons, 1, 2 and 3. Okay, that's why 3 C13 NMR signals are appeared in this molecule. That's why here option 1 will be the correct answer for it. Okay, next one, among the following, the compound which have the lowest energy barrier for cis-trans isomerization is. Okay, right, first we need to look at the given 4 options. So if you look at this, you need to get an idea about the ring stabilizations. Okay, right, when you get the idea about ring stabilization, you can get idea about aromatization of that particular ring. Okay, if you look at the third option here, in that we have 5-member ring and other one 7-member ring. Okay, in the 5-member ring we have already 2 double bonds. If this 5-member ring if it get negative charge, then 6 electrons are there in the ring, and which is planar and which is following Huckel's rule. Okay, Huckel's aromatic rule, 4n plus 2 rule, 4n plus 2 pi electronic rule. That's why it is aromatic in nature. Aromatic compounds are stable. Okay, that means the 5-member ring must get negative charge here. At the same time, the 7-member ring with 3 double bonds. 3 double bonds means simply it is having 6 pi electrons, and if this carbon gets positive charge here, okay, if that get a positive charge, then the delocalization is possible with that positive charge with the 6 double bonds in it. Okay, that means it is also fulfilling all the requirements for the aromatization and it is getting stability. Okay, as we know, whenever double bond is there and a single bond is there between 2 carbons, a single bond, that means a single bond containing molecules can be easily rotate. Okay, that means the energy barrier is lowest for the single bond molecules when we compare with the double bond containing molecules. So in the given 4 options, the third one where the 5-member ring tries to get negative charge and 7-member ring tries to get positive charge, that means we can represent with that a single bond between these 2 5-member and 7-member rings with the positive and negative charges on them. Okay, then the single bond can be easily rotated and this trans form can convert to cis form and cis form can be converted to trans form. That means the lowest energy barrier is possible in third option. Okay, next one, the IUPAC name of the compound given below is. Okay, just observe the structure of the given compound. So we need to give the correct IUPAC name for it. So just check the lectures on IUPAC nomenclature in your course to get the complete information how to give IUPAC nomenclature for the given organic compound. Yeah, here first we need to look for the suffix, that means the priority of the main functional groups. Okay, here we have hydroxy group, alkene and hydroxy group. 3 functional groups are there. Which has the highest priority in these functional groups? Hydroxy group gets the highest priority, followed by double bond, followed by chlorine. That means we need to give the highest, that means a suffix for that hydroxy groups. Okay, that means hydroxy group as a suffix. Here we have 2 hydroxy groups, that's why we need to give diol. Okay, right, and just look at 1, 2, those, so total 6 carbons are there. That's why here we need to give 1,6 diol. That means if you, so after giving the suffix, we need to look at for the other functional groups. Now here we have double bond and chlorine. So chlorine is nearest to this hydroxy group Okay, so that's why we need to start numbering from this hydroxy group 1, 2, 3. That means a third carbon we have the functional group, that is chlorine. Okay, so we should not give numbering from this side, because it is not having nearest functional group. Okay, this hydroxy group doesn't have any nearest functional group, like that means substituted functional groups. Okay, so double bond is inbuilt in it. Okay, double bond in the parental chain. That's why we need to give the priority for the substituted functional groups first. So here this hydroxy group is having chlorine functional group which is near to this hydroxy group at third place. So we need to give numbering from this hydroxy group. Okay, so when you give that, so chlorine gets third position. Okay, and this double bond, so at the second carbon we have double bond. Okay, at the fourth carbon we have double bond. So here we need to give 3 chloro hexa 2,4 diene 1,6 diol. After that, here we have given with EZ nomenclatures in it. We need to check for the EZ nomenclatures, which should be given at the first in prefix. Okay, right. So we need to look for this. So at the second carbon we have a double bond. We need to look for the EZ nomenclature on it. Okay, so if you look at this carbon, that means this one, on that we have chlorine and one double bonded carbon. So chlorine gets first priority and double bond gets second priority. So 1 here and 2 here. Okay, and on this another carbon of this double bond we have hydrogen, and here we have carbon. So carbon gets first priority and hydrogen gets second priority. That means 1 and first priority groups are same side. Okay, that's why we need to give Z for it on the second, that means the double bond on second carbon. So 2Z is the correct one. Okay, and if you look at the fourth, that means a double bond on fourth carbon, so just give the priority. So this carbon gets first priority, so give the number 1 here, and hydrogen gets second priority. And here we have hydrogen, and here we have chlorine with the double bond carbon. So first priority here and second priority here. So just look at here, it is opposite. That means simply priority groups are opposite to each other. Now we need to give E nomenclature for the double bond. So 2Z 4E. Now 2Z 4E 3 chloro hexa 2,4 diene 1,6 diol is the answer. So second option will be the correct answer for it. Okay, right. And next one, the major product formed in the following reaction is. So just look at the given reaction here. You need to give the correct answer. And if you look at the reactant, so many gets a doubt by just looking at the 4 options which are given in the problem. Okay, right. As we know, sodium methoxide can act as nucleophile. That means methoxy group can attack in 2 possible positions. Okay, one can think the methoxy group can attack at the 2 positions. So which will be the correct answer for the given problem? Okay, so this is the confusion arise in the minds of aspirants on the examination hall. Okay, now we need to think more deeply here. Okay, right. As we know, methoxy group is a nucleophile and which can attack on electrophile. That means electrophilic carbon on the given reactant. Now here we have 2 electrophilic carbons. One is here and one is here. So which one is more electrophilic? Here this carbon is more electrophilic because which is directly connected with the more electron withdrawing group nitrogens. Okay, so that's why methoxy group, that means nucleophile, can attack on this electrophilic carbon, where this chlorine can cleave as Cl minus. Okay, so that's why this will be the correct product. Just check the options, that is third option will be the correct answer for this problem. Okay, right. And next one, the constituent amino acids present in the following dipeptide respectively are. So we need to look at the given dipeptide at the link of simply C double bond O NH. Okay, that means peptide bond. Okay, we need to look at the peptide bond in the given dipeptide, and we need to just cleave that peptide bond. Okay, so C double bond O NH. Whenever you cleave that, we can get these 2 amino acids. Okay, so this amino acid is aspartic acid and other one is lysine. Okay, right. After that we need to look for the RS nomenclature for it. So we need to give RS nomenclature on this. So this is the chiral carbon. Just give the RS priorities for the groups. So N nitrogen gets the first priority, so which is having 1, and carbonyl group gets second priority, and this gets the third priority, and here is the hydrogen which is having fourth priority, which is above the plane. Okay, just remember that whenever chiral carbon contains least priority group above the plane, we need to give opposite nomenclature for the priority order. So just look at here, the priority is anti-clockwise direction. Okay, the priority is anti-clockwise direction with the least priority group is above the plane on the chiral carbon. That's why we need to give R notation for this chiral carbon. So here aspartic acid with R notation. So here answer must be 1. Okay, and look at this lysine chiral carbon which is having chiral carbon. We need to give RS nomenclature for it. In that case, nitrogen gets first priority, so 1, second for this carboxylic group, and third for this. Okay, so for this carbon, so here the least priority hydrogen which is backside to it. Okay, that's why whenever least priority group is backside on the chiral carbon, there is no need to change the priority order. We need to give direct RS nomenclature based on the priority rule. Okay, so it is the priority is simply anti-clockwise direction. That's why we need to give S connotation to that particular lysine. Now just look at the first option, R aspartic acid and L lysine. So option 1 is the correct answer for this problem. Okay, next one, a suitable organocatalyst for enantioselective synthesis of a weiland-miesleir ketone A is. Okay, so here we have given with proline, menthone, guanidine and plus binol. Okay, so just look at all of the given options. Here if you look at the reactant to product, this is the Robinson annulation. Okay, simply that means whenever we have a base in this reaction, base can abstract proton from this methyl group, okay, and which can form enolate and which is going to attack on this carbon of the ring, okay, and which make this 6-membered ring with that alpha beta unsaturated ketone. Okay, right. So here involvement of Robinson annulation, and here the base must be optically active. Okay, to give the optically active product, the base must be optically active. Okay, for this the proline, okay, L-proline is the best one to use here to produce optically active weiland-miesleir ketone A. Okay, so option 1 will be the correct answer for it. Next one, for acylation with acetic anhydride, triethylamine and oxidation with chromium trioxide of the trans and cis alcohols A and B, the correct statement is A undergoes acylation as well as oxidation faster than B, and B undergoes acylation as well as oxidation faster than A, and A undergoes acylation faster than B, whereas B undergoes oxidation faster than A, and fourth one, B undergoes acylation faster than A, and whereas A undergoes B undergoes oxidation faster than A. Okay, so just check it, all these options, and just check the mechanism here. We have given with a planar form of 6-membered ring with 2 groups, 1 hydroxy group and 1 bulk group. Okay, so these two are 1,4 positions or each other on this planar 6-membered cyclic hexane. Okay, so we need to convert this transform, okay, 1,4 trans cyclohexane into chair conformation. Just remember that, and already we have lectures in our courses that, so whenever we convert the cyclic cyclohexane into chair conformation, so if 1,4 groups are trans to each other, they should be equatorial or axial. Okay, this bulk group must be equatorial on chair conformation to escape from the steric repulsions. Then other hydroxy group must also be equatorial. Okay, because the cyclic planar form is trans at 1,4 positions. Okay, right. After that, the lone pair of electrons on hydroxy group can attack on this anhydride to produce the product. So here you can see the acylation is very easy here. That means there is no steric repulsions in this trans product A. Okay, whereas if you observe cis product, that means here also two groups are 1,4 position with cis to each other. Now we need to convert this into chair conformation. In chair conformation, 1,4 cis groups on cyclohexane must be converted to equatorial axial or axial equatorial. Okay, and here the bulk group must be equatorial, then the hydroxy group must be axial on chair conformation. Okay, right. Now the lone pair of electrons on hydroxy group can attack on chromium. That means here oxidation is very easy on cis form of this given compound. Okay, if you look at the acylation on this cis compound, what happens? The lone pair of electrons on this axial hydroxy group can attack on this acyl group, and here is the formation of product with acyl group. Okay, so there is the steric repulsions are possible in the product. That's why acylation is not possible in cis form of it. Okay, only oxidation is the best to possible on cis form, and acylation is the best one to form. Acylation is the best one on the trans form of it. Okay, right. Thank you.